All right, this should be our last video in equilibrium. We're looking at question F. Imagine you have a system that's already at equilibrium. We're going to consider what happens when we disturb this system, when we do something to the system. And we're looking up here at this picture. If we add more reactants to the mixture, the equilibrium will shift to the right. If we add more products to the mixture, however, the equilibrium will shift back to the other direction, to the left. If I remove reactants from the mixture, the equilibrium is going to shift again to the left. If I remove products from the mixture, the equilibrium will shift to the right. When there's a shift in the position at constant temperature, will the value of K be changed? No. K depends only on the reaction, the individual things that are reacting, and the temperature. So the only way that the value of K will be changed is by changing the temperature. All right, now we look at part G. If an equilibrium system contains one or more gases, the volume of the container can be increased or decreased. The system will respond according to Le Chatelier's principle, and we are referring to this figure right here. So if we increase the pressure on the container by decreasing the volume, the equilibrium will shift towards the side of the equation that has the fewer moles of gas. If you decrease the pressure on the container by increasing the volume, the equilibrium does the other thing. It shifts towards the side of the equation that has more moles of gas. I can virtually guarantee you will see a problem like this on the exam, either in multiple choice or free response side of it. All right, question H. Explain why changing the pressure on the equilibrium system shown below has no effect. All right. This is because I've got 2 moles of gas on each side. So that doesn't really have an effect on the equilibrium because there's no side that has an advantage over another side by changing the pressure. All right, question I. Suppose an equilibrium has been established at 100 degrees such that the concentration of N2O4 is 2 molar and NO2 is 0.65. I reduce the volume of the container by half, and we need to calculate the new concentration of each of the species at the moment the volume is reduced. So the first thing we're going to do is calculate the value of Q at that moment. So Q is just the concentration of NO2 squared divided by N2O4. We plug in our values and we get 0.21. So Q is equal to K. We are at equilibrium. Now, if I reduce my volume by half, then the pressure must increase by 2. I'm sorry, if the volume gets reduced by 2 or cut in half, then the pressure would double. So now Q is going to be equal to double 0.65 is 1.3 squared divided by double 2 or 4, and now I get 0.42. So in which direction would the reaction shift in order to reestablish the equilibrium? Well, at this point, Q is larger than K, so the equilibrium shifts back to the left, or the side with the fewer number of moles. All right, now we need to calculate the concentration of each species when the system reaches equilibrium. So we set up our rice box, we have our reaction. Our initial concentrations here are 4 and 1.3 after we do the volume change. So my concentration goes up X and goes down by 2X. And when I look at the equilibrium position, I have 4 plus X and 1.3 minus 2X. I plug that into my Kc equation. I get a quadratic. I have 2 answers for my quadratic, but I can see that if I have 1.2, that's going to give me negative numbers or numbers that don't make any sense. So I stay with 1.34, and therefore my concentration of N2O4 is 4.18 and NO2 is 0.94. Suppose that the pressure on the equilibrium system is increased by adding an inert gas like argon. will the position be affected by this change? And the answer is no, because this doesn't change the pressure of the gases unequally. Argon doesn't react with anything. So there is no change in the equilibrium position. Now we've got a series of fill in the blanks. If a reaction is endothermic, we can treat heat as a reactant in the chemical equation because it's as if we are adding heat to the reaction to get it to occur. And of course, if it's exothermic, it's a product. So when the temperature of a system is increased, the system responds as if we added more reactants to an endothermic reaction, or if we had added more products to an exothermic reaction, and the equilibrium shifts in that direction that consumes some of this excess heat that's added. So when the temperature of an equilibrium system is decreased, the system responds as if we've removed some of the reactants from an endothermic or some of the products from an exothermic, and it will shift in the direction that produces more heat. So now we need to fill in the table below. And that's on the next page, the next slide, but you see it in your notes. I've got an endothermic and an exothermic reaction. All right, so this is just taking the results from the previous discussion and sort of filling in the blanks here. So for an endothermic reaction, if I increase the temperature by adding heat, I shift to the right and the value of K will increase. For an exothermic reaction, I shift to the left. The value of K will decrease. Now, the opposite is true if I decrease the temperature. Endothermic will shift left and the value of K will decrease. An exothermic reaction will shift to the right and the value of K will increase. All right. Question O. You may recall that in part A of the section it was observed that increasing the temperature of the ammonia reaction mixture caused the percent yield to go down, to decrease. Now we're going to look at table 15.2, which you can see. Is the synthesis reaction for ammonia endothermic or exothermic? Well, when T increases, you can see the value of K goes down. Therefore, the shift is to the left. P, a catalyst lowers the activation energy barrier. This affects the EA, the activation energy, for both the forward reaction and the reverse reaction. Therefore, adding a catalyst to an equilibrium system will have what effect on K? The answer is not really any effect on K. But what it does do, it increases the speed with which this equilibrium is reached. We haven't talked about kinetics yet, but we will. So now we're going to imagine a chemical system for the following reaction. A goes to B, and we're given a little graph here, which shows the concentration of the product B over time. One of these curves represents a catalyzed pathway, and the other an uncatalyzed pathway. And the question is, does the concentration of B change at equilibrium as a result of a catalyst being added? And then we need to label the diagram. Well, again, we see that the catalyzed reaction is the one that reaches equilibrium condition sooner rather than an uncatalyzed. They both come to the same value. So we wouldn't expect the concentration of B to change as a result. We just expect a different time to occur. All right, and that concludes our notes for the equilibrium chapter.